Now a function is a relation between a set called a domain and a set called a codomain. Each element of the domain is assigned to exactly one element in the codomain. So a keyword here is each element of the domain. So in this set, this domain, we have 5 elements, and you can see that an arrow leaves each element. That must be the case for a function. We cannot have an element sitting here with no arrow leaving it. And each element is assigned to exactly one element in the codomain. So that means that we can't have 2 arrows leaving an element. So for example, if we take this element in the codomain, we can't have this situation. Okay, so this element must be assigned to exactly one element. And if this is the case in this picture here, well, we have this element assigned to 2 elements, and that's not allowed for a function. So we get rid of that. So we could sum up our definition of a function this way. Exactly one arrow leaves each element in the domain. Now notice that there are elements in the codomain that don't have an arrow pointing to them, and that's allowed. I haven't given names to these elements, but that's not too relevant here. We're just looking at the general picture of a function. Let's suppose that we give a name to this element here. Let's say this element is n. Well, its image will be f of n. If this element is called p, well, its image is f of p. But you can see in this case that f of n is equal to f of p. Here is an example of a relation that is not a function. And the reason that this is not a function is that this element in the domain has no arrow leaving it. Here is another example of a relation that's not a function. You can see that 2 arrows leave this element. Here's a relation that is not a function. If we define the square root of a number to be either its positive or negative square root, well, you can see that if our domain consists of these 2 elements, the number 9 and the number 25, well, the number 9 gets mapped to plus 3, but it also gets mapped to minus 3. Similarly, the square root of 25 can be either plus 5 or minus 5. Here is the graph of the square root of x. Well, this is a rough sketch, and you can see that x and y axes are not to scale. But the point here is that at the value 9, x equals 9, we have 2 points on the graph. So, if we draw a vertical line through 9, the vertical line cuts at 2 points. And for a function, we want a vertical line to cut at just 1 point. Now, we could adjust this relation so that it becomes a function. We could just consider the positive square root. Okay, we could put it in a plus sign to emphasize that. Or in general, we just leave out the plus sign. And we assume that when we take the square root of a number, we're just getting the positive square root. Okay, so in this situation, you can see that we do have a function. Only one arrow leaves 9. We just take the positive square root of 9. And here's the graph. If we take any vertical line, it cuts the graph at just 1 point. So if we take a vertical line through 9, it cuts it at 3. If we take another vertical line through 25, it will cut it at 5, and so on. Now, it doesn't matter that these 2 points have no arrows pointing to them. This is still a function. Okay, exactly 1 arrow leaves each element in the domain. There's only 2 elements in the domain, so there are just 2 arrows leaving. Now, this is just one particular use of the square root to give a function. I could have put in another element here, say 36, and I'd have to stick in another element into this codomain to get a new function. So this is a new function involving the square root. Okay, because I've changed the domain. I've now got 3 elements in the domain. this new element 36 and a new element over here in the codomain. So basically we have a new function, but it just involves getting the positive square root. Now let's look at some types of function. The first type of function we will consider is a surjective or onto function. So this is a function for which each element of the codomain is the image of some point in the domain. So another way that we could define surjective function is to say that every element in the codomain has an arrow pointing to it. So we don't have an element out here with no arrow pointing to it. So all the elements in the codomain are used up, if you like. F equals the square root of x, where we are just taking the positive square root, is a surjective function from the positive real numbers to the positive real numbers. The positive real numbers, including 0 here, is a continuous infinite set. Okay, unlike the last examples where we're just dealing with a finite set, and just discrete elements. So obviously it's going to be difficult to represent this the positive real numbers in our domain in this form here. But we look at individual elements. Now, since this is a surjective function, we should find that every element in the codomain has at least one arrow pointing to it. So for example, let's take the element 5 in the codomain. That's a positive real number. It's obvious that we have an arrow pointing to it, and the input must be 25. The input for this function must be 25, and the output is 5. Okay, so it's true no matter what element we take in the codomain, no matter what positive real number we take, we'll always find at least one arrow pointing to it. So for example, let's take the element 31.5. Well, there's an arrow pointing to it, and this point here is just 31.5 squared. Okay, because if we take the square root of 31.5 squared, we get 31.5. Okay, so all the elements in the codomain are used up, so we have a surjective or onto function. Here is an example of a function that is not surjective. It's a function from the natural numbers, that is the positive integers including 0, to the set of real numbers. Now I've indicated 3 elements, the first 3 natural numbers actually in this domain, and when we input these values into our function, we just multiplied the values by 3. So for example, f of 0 is 3 times 0, which is 0. F of 1 is 3 times 1, which is 3. F of 2 is 3 times 2, which is 6. But you can see that there are some real numbers, the domain is the set of real numbers, which are not 3 times a natural number. So for example, the number 2 is not 3 times any natural number. I could put in some more values like minus 7.5. Minus 7.5 is not 3 times some natural number. So you can see that all the elements in R are not used up. So this is not an onto function. The next type of function is an injective function. This is a function for which elements in the codomain are the image of exactly one element in the domain. So informally, we could say that an injective function is a function for which only one arrow points to an element in the codomain. You see, these elements here have only one element pointing to them. Well, you can see an element here with no arrow pointing to it, but that's fine. This function doesn't have to be surjective. Here is an example of a function that is not injective. You can see that 2 arrows are pointing to this element here in the codomain. Now we could make this an injective function by taking this arrow here and pointing it to this element here instead. Now you can see that only one arrow points to elements in the codomain. So now we have an injective function. Here is an example of an injective function. The function f of x equals 2x, and this function is such that set A maps onto set B, where set A consists of the three elements -7, -3 and 5.1. Set B consists of these elements here, -14, -6, 10.2 and -81. Okay, so you can see that elements that have arrows pointing to them have only one arrow pointing to them. You can see also that there's an element here with no arrow pointing to it, so this is not a surjective function. Here is an example of a function that is not injective. It's the function f of x equals x squared, where the domain is the set of real numbers and the codomain is also the set of real numbers. It's easy to see that this is not injective by considering the values -1 and +1 in the domain and squaring them. Okay, so -1 squared is +1, but +1 squared is also +1. So we have two arrows pointing to this element, which means that this function is not injective. We have infinitely many examples, of course, but we only have to show one example of two arrows pointing to an element in the codomain to conclude that the function is not injective. Notice that on the graph, if we take a horizontal line through 1 on the y-axis, this horizontal line cuts the graph at more than 1 point, cuts the graph at 2 points. So f of -1 equals f of 1, which is +1. In general, a horizontal line cuts the graph of an injective function at 1 point at most. So here is an example of an injective function, the function from the set of real numbers or to the set of real numbers. It's a line, straight line. It's easy to draw, you know, we could just pick 2 points. Like if we let x equal 0, we get that the line cuts the y-axis at +1, and we could pick another value for x. The slope of this line is 2, so that means if we pick any point, say this point here, increase x by 1, we have to go up 2 units to meet the line. Okay, it's got a positive slope. But anyway, the point is that if we draw any horizontal line, it'll cut the graph at most 1 point. See, this line here cuts the line here at just that 1 point. So that means that you know, we have a value of x corresponding to that point, and we just have one image. Well, we could say that the image point has only one origin point. Now let's consider a different function. It's got the same rule as before. The rule is input x multiplied by 2, add 1. But you can see that the domain and codomain are different. The domain is the set of integers denoted by z, and the codomain is also the set of integers z. So as a reminder, here's the set of integers. All the negative integers, 0, and then all the positive integers. So how do we draw this function? Well, you know, x can only take on these values here. So for example, let's suppose x is -2. Well, we plug -2 into this, and we get 2 times -2, which is -4, plus 1, which is -3. Let's take -1. Okay, I'm not going to show -3 or -4, okay? I'll just show a small subset. of z. So 2 times minus 1 is minus 2, plus 1 is minus 1. So that's about here. So you can see that our graph is not going to be a continuous line or curve. It's going to consist of discrete points. As for f of 0, we're going to get 0 plus 1, which is 1. And so on. Now again, this is an injective function, because if we draw any horizontal line, it'll cut this graph at most one point. Well, this particular horizontal line cuts it at no point, but that's okay. It doesn't have to cut the graph. See, it cuts the graph at one point at most. So it could cut the graph at no points, or it could cut the graph at exactly one point. If we draw the graph here, draw a horizontal line here, you can see it cutting the graph at just this one point. But it's certainly not going to cut the graph at 2 points. So the graph, in our case, is not a continuous curve, it's a set of discrete points. Another way to look at an injective function is that it's a function for which f of a equals f of b implies a equals b. So for example, suppose that this element in the codomain is f of a, and it's also f of b, where a and b are some pair of elements in the domain. Well, if the function is injective, a and b refer to the same element. So this element here is a, and it's just the same as b. So just one arrow goes from a to f of a. If the function was not injective, well, we could have two different elements a and b in the domain. Okay, we don't want this situation. We don't want a to be different from b. We want a to equal b. So if we have a new element, a different element in the domain, that that doesn't get mapped to this point. It gets mapped to some other point. So let's apply this approach to the function that we just did, which is 2x plus 1, a mapping from z to z. So suppose we have a point in the codomain which is the image of a and the image of b. We want to show that a is equal to b. So that means there's only one arrow pointing to this point. Well, we just work out f of a and f of b, and that's straightforward here. F of a is 2a plus 1, and we want to set it equal to f of b, which is just got by plugging b in for x, so that's 2b plus 1. And we want to deduce from this that a is equal to b, and that's very easy here. We just subtract 1 from both sides to get this, and then we divide both sides by 2, and straight away we conclude that a is equal to b. So it's very straightforward here to show that if f of a equals f of b, then a must equal b. So a and b are the same element, so it could be this element here. Let's apply this approach to f of x equals x squared and show that it's not an injective function. Here the domain is R and the codomain is also R. So we imagine that we have two elements a and b such that f of a is equal to f of b. So we want to prove or disprove that a is equal to b. So let's work out f of a and f of b. Well, f of a is just a squared. F of b is b squared. So does this equation lead us to the conclusion that a is equal to b? Well, actually it doesn't lead us to that conclusion. It does not imply that a is equal to b, and that's easy to see. Suppose that a was 2 and b was minus 2. Well, if we square both of these numbers, we get plus 4. So it is true that a squared equals b squared for these two values of a, for these values, a and b. But you can see that these are not the same. A is not equal to b here, even though if we square them, we get the same result, plus 4. You see, if we work out a from this equation, if we take the square root of both sides, we see that a could be plus b or it could be minus b. So, we could have used a equal to b, which would have shown that the function is injective, but a could have been minus b, and we would have got f of minus b equals f of plus b. But these two are not the same, well, unless there's 0. But in general, these are not the same. Minus b is not equal to b, even though the squaring gives the same result. The last type of function is a bijective function. Now this is a function that is both injective and surjective. So you can see here that an element in the codomain has at most one arrow pointing to it. Okay, you can't have two arrows pointing to an element in the codomain. So that makes this function injective, and you can see that all the elements in the codomain are used up. All elements in the codomain have an arrow pointing to them. In particular, for a bijective function, you can see that the number of elements in the codomain must equal the number of elements in the domain. Sorry, I said that the wrong way around, but you can see that both of these sets have the same number of elements. Here is an example of a bijective function. The function f of x equals x plus 2, where f takes the set of real numbers to the set of real numbers. You can see that if we draw a horizontal line anywhere at all, the horizontal line always cuts the graph at exactly one point. Now, to be specific about this, we're talking about a horizontal line that passes through points in the codomain. Now the codomain in this function is R, the set of real numbers. So it's all of the y-axis actually. That's the codomain. So the image of x is a value which we could call y. Y is x plus 2. But that value of y belongs to the set of real numbers. Okay, so we draw horizontal lines through points in the set of real numbers. So that's basically all the points on the y-axis. So if we take any point at all on the y-axis, that means any point in the codomain of the function, and draw a horizontal line, we will cut our graph at exactly one point. So that tells us that we have a bijective function. Now we could change this function into a function that's not bijective by changing this domain. I'll change it to n, the set of natural numbers, and let's look at the graph. So we can only get the image of these natural numbers, 0, 1, 2, 3, and so on. Okay, so we plug them into this. So if we plug 0 in, we get 2, just like before. If we plug 1 in, we get 1 plus 2, which is 3. When we plug 2 in, we get 4. When we plug 3 in, we get 5. So you can see now that our graph is not a continuous straight line. It's an infinite set of discrete points. Okay, it continues on this way, but it doesn't continue on the other way. So now you can see that if we take a horizontal line, it doesn't necessarily have to cut this graph at exactly one point. So this particular horizontal line cuts the graph at no point. So that means the function is not bijective. Okay, the horizontal line must cut at exactly one point, not no points, not 2 points or more, but exactly one point. So let's look at the Venn diagram for this function. So in the domain we have the set of natural numbers 0, 1, 2, etc. We have the set of real numbers here. Okay, I'm not going to attempt to indicate those because it's a continuous infinite set. Okay, I was going to look at the value 3.5 in here. You can see that no arrow lands on this point. So we found an element in the codomain which has no arrow pointing to it. So that corresponds to a horizontal line, this horizontal line here, passing through 3.5. It does not cut the graph. If the graph had been a continuous straight line, it would have cut at 1.5, but 1.5 does not appear in our domain. By the way, this function is injective. Elements that have arrows pointing to them have only one arrow pointing. You don't have two arrows pointing to an element in the codomain. So only one arrow points to an element. Of course, there's some elements with no arrows pointing, so it means that the function is not surjective. Not all these elements are used up. So it's injective, but it's not surjective. So that means that it's not a bijective function.